Hello friends, welcome back to Quantum Quandary. Today we'll be looking at the Brachistochrone problem. A Brachistochrone is the curve of least time traveled by a particle from one point to another. So if we have this coordinate system y and x, and we have a gravitational field g, just constant, like in the planetary approximation on Earth, for example, and we have a particle at y equals 0, x equals 0, and we want it to reach x0, y0. So we want it to reach here. What kind of curve do we need here, which the particle would roll on? Of course, it's frictionless, it's an approximation. What is the optimal shape of this curve, such that we get there the fastest? Now, we talked about calculus of variations. Indeed, we want to minimize the time traveled, so we form an integral that depends on the time, time dt. But we are looking for the shape of this function, the shape of this curve, and we can express the curve as y of x or x of y. It really doesn't matter, since it's a curve, spatial curve. So we'll do what is simpler for us. Now, if s is the integral of dt, we need to find dt in terms of x and y and their derivatives with respect to each other. Well, dt is nothing but dt times 1, and 1 is nothing but ds over ds, where ds is this line element, which, as you'll recall in Euclidean geometry, is the square root of dx squared plus dy squared. And now here, of course, we can factor out one of the differentials and leave a derivative of the other. And ds by dt, let me just rewrite this. So this is ds times ds by dt minus 1, right? 1 over this. Now this is just velocity, the modulus of the velocity, which would be equal to the square root of the derivative of x squared with respect to time and y squared with respect to time. But we can find something else. Since energy is conserved here in this problem, there's no friction, there's no heat, there's no external field except for the potential, then we have that the kinetic energy T plus the potential energy V is constant. And that means that mv squared over 2 plus mg, and then notice that mg is weaker the smaller y gets, so I'm going to write it as this, mg minus y. Actually, is that even good? It is good. Yes, as minus y. No, it isn't good. I would need to draw it like this. Yes, that's the thing. So I want y to be increasing like this. In this case, it's minus y. So if in negative y over here, we would have positive potential energy. This is where our potential energy is 0. So this is V equals 0. Yep. And this is why we get minus y. So this would be constant. Now, if that's constant, then we can just plug in y equals 0 and get the value for mv squared over 2. So what I mean is get the value for the constant. So we know that the velocity of 0 is 0. This is one of our initial conditions. V of time 0, that is, V of time equals 0 is 0. And let me just note that x of time equals 0 is 0, and y of time equals 0 is 0. So both x and y are increasing with respect to time. So if the velocity at t equals 0 is 0, and y of 0 equals 0, then that means that the constant is equal to 0, right? Because we have 0 plus 0 equals constant. And this means, in turn, that mv squared over 2 is equal to mgy. So we have that v is just a v of y, okay? Velocity completely can be expressed just through the y variable. So here, let's just express it then. So v is the square root of 2gy. All right, and then we're going to want to use this. So we're going to be putting our v in there. And we have the action equal to the integral of, so we have ds over v. Now ds is dx squared plus dy squared. I'm leaving it in this format intentionally for now, 2gy. Now you'll notice that I can take 1 over square root 2g in front. It's just a constant. We don't care about it when we're minimizing, so I'm not going to keep writing it. Here we have the square root of y, and now we need the differential to integrate over. Now, it is going to be much simpler to treat this as x of y instead of as y of x. You can try both ways, and it's not much different, but it is going to be simpler for our calculations. So what I'm going to do is I'm going to take out dy, and I'm going to treat y as the independent variable. So in the square root, I'm going to have x prime squared plus 1, where x prime is defined to be dx over dy. There we go. And now, if we recall the Euler-Lagrange equations, for the variation to be 0, the variation of the action, we need to have, and this is our Lagrangian, the whole thing, in between the integral and dy, we need to have that d by d, the independent variable, so this is where we put y, partial Lagrangian by partial x prime minus partial Lagrangian partial x equals 0. So this is what needs to hold. Well, we need to differentiate everything, but luckily this part here is just equal to 0. So what we get is that d by dy of the partial of the Lagrangian with respect to x prime is equal to 0. That just means that this quantity is a constant. So let's call it c. Let's call it c, and let's differentiate it. The square root is going to be going down, x prime squared plus 1, and square root y, 1 over, and of course we would have a 2, which is going to get lost, so x prime, this is equal to c. And now we square both sides, and multiply with the square roots, so we have x prime squared is c y x prime squared plus 1. Okay. We can express with respect to x prime squared. Let's keep squared. 1 minus cy equals cy, and x prime is the square root of cy, 1 minus cy. There we go. Now this is integrable. A lot of people like to express this with respect to an independent parameter, phi. So we parameterize x and y with respect to phi. If I were to do this immediately, it would be sort of like an ansatz, like I'm suggesting the solution. Now I could do that, but I seem to prefer actually solving it first. Since it is a solvable one, we just have the dx is the square root of cy, 1 minus cy dy. And we can solve for x here. It does take a little bit of a long time, and I'm worried that I'm gonna make a mistake. Let's see how it turns out. Okay, so integrate both sides, and I'll just be looking at this. Let's call that I. So I is the square root of cy over 1 minus cy dy. First of all, I'll multiply by c and divide by c. So I could have cy is equal to, when I have sine squared theta, let's say, so that this part becomes cosine, okay? So cy is sine squared theta. That means that dcy is 2 sine theta cosine theta d theta. Okay, which is sine 2 theta, by the way. So the integral is 1 over c integral. Let's put dcy first. So that's 2 sine theta cos theta d theta. And then we have cy is sine squared theta, so that's sine theta. And 1 minus cy is 1 minus sine squared, which is cosine squared. The square root is cosine theta. So this part and this part dies, and we have 2 sine squared theta. Now note that 2 sine squared theta is, well, 1 minus this is cosine 2 theta. So that means that 2 sine squared theta is 1 minus cosine 2 theta. So we have 1 over c, the integral of 1 minus cosine 2 theta d theta. And that's equal to theta over c. Oh, okay, 1 over c. Theta minus 1 over 2 sine 2 theta. We can write sine 2 theta as 2 sine theta cosine theta, like this. Okay, there we go. That's it. That's the whole thing. So 1 over c, theta minus sine theta cosine theta. And plus some other constant, huh? Guess we don't need it, do we? I guess I could always assume that it doesn't exist. Let's include it for now, and I'll see. In any case, so we have that sine theta. Sine theta is square root cy, and cosine theta is then just 1 minus sine squared theta. So this integral with respect to y, with respect to cy, is 1 over c. So theta is the inverse sine inverse of square root cy. And then minus sine theta is cy. And cosine theta is 1 minus sine squared, which is 1 minus cy. All square root, yeah. Okay. So, and that's equal, plus k, and that's equal to x, right? Because the integral of dx is just x. So this is our function x of y, parameterized, and it doesn't look too pretty. If I'm honest, you can't really see that it's a cycloid, which is supposed to be the solution from this. But when you plot it in Desmos or something, you get a fairly nice solution. This one is gonna hold only for y less than 1 over c, right? Because of the square root. But y is always positive, which is good, right? So y is always positive in our problem. You never fall upward. So at least that's not a problem. Yep. Now we can try this other ansatz. The ansatz, now I'm not sure how they label x and y. I did look at this ansatz. So where are we? We want to look at this, right? I believe that they say that y is phi minus sine phi and x is phi 1 minus cosine phi. We would also need to have the identity of dx by d phi, because dx by dy is dx by d phi by dy. Okay, I think I'll leave that for another video then. I'll parameterize this and show you. But for now, this is the equation of the Brachistochrone. And without this I, obviously. That's it. That's our curve of minimal time. I guess it would be nice to look at it, but you're going to have to type it into Desmos yourself. Thank you for watching. Bye-bye.